Hey ChemStars, Chapter 9 Stoichiometry is drawing to a close, and right now we're going to work on the PhET lab instruction video. So our PhET lab, your Chapter 9 notes, video lecture should be finished, Chapter 9 homework practice problem should be finished or almost finished, and then we're going to be working on the PhET virtual lab. And then after that, you're going to take your objective check on limiting reactants and percent yield. So this lab, there's the lab worksheet here. If you don't have a copy of that, you can print it out, or you can do it on some scrap paper, or make a digital copy and type it if you want. Macaulay students, Vanderwally students, you should have a paper copy of this. And I'm working on the PhET lab instructional video right now. So the first thing is we've got to read the lab introduction, then define the vocabulary terms. Then we're going to go to the lab link. Okay, so let's get started. So let's read the intro. So introduction. When we bake or cook something, we use a specific amount of each ingredient. Imagine if you made a batch of cookies and used way too many eggs or not enough sugar. Yuck! In chemistry, reactions proceed with very specific recipes. We've been talking about that all chapter. The study of these recipes is called stoichiometry. When the reactants are present in the correct amounts, the reaction will produce products. What happens, though, if there are more or less of some of the reactants present? So what is going on then? And some of you should be saying, limiting reactants, excess reactants. So before you begin, please define the following. And I've linked those on the slide, so you can copy them down from right here. Limiting reactant, that's the thing that is totally consumed. Or you also could say, it's all used up. When the chemical reaction is complete, it's called limiting reactant or limiting reagent. Those two are synonyms. The excess reactant, which we'll abbreviate excess, and limiting reactant we abbreviate LR, the substance that is not used up. So it is not used up. That means that there's leftovers. When the reaction is finished, that's called our excess reactant or the excess reagent. Remember, reactant and reagent are synonyms. So part 1, there's going to be a simulation of a 2-reactant synthesis reaction. In this case, one reactant will be limiting while the other will be in excess. We're going to take some time to figure out how the simulation works. We're going to be working on part 1, making sandwiches, and then we're going to try and fill out this chart. Okay, so let me go back to our slides. Okay, so we're going to work on this, and when we get to part 2, we've got to come back and make a note about reading moles and molecules, but if you've watched all your lecture videos, you should be good at figuring all that out. Okay, so let's look at the sandwich simulation. So let's just take a minute here and let's look at, okay, here's our recipe for sandwiches. We've got 2 pieces of bread, 1 piece of cheese, makes 1 sandwich. If you want to get fancy, you can make a meat and cheese sandwich. We got some bologna there, some ham. We need 2 pieces of bread, 1 bologna, and then 1 piece of cheese. Let's just play around with this. So let's say I have a piece of each. Do I get a sandwich? Nope, because I need to have 2 pieces of bread. And if I do that, now you can see I've got 1 whole sandwich. But what if I add a whole bunch of extra meat? Do I get any more sandwiches? No, and that shouldn't surprise you because we have to add other things too. Okay, well now let's add some cheese in. Do I get any more sandwiches? Nope, because I was limited on the amount of bread I had. So let's just see how many sandwiches I can get if we keep going. Now, the simulation limits me here at 8. I can't go above 8 on this one. Okay, so let's go back and check our directions. So, we're going to be using just the bread and cheese example. So let's just set this up a little bit. So bread used, cheese used. These are my reactants. And then right here, this is my product. And then these are the excess. These are the leftovers over here. So let's do 5 and 5 and see what happens with that. So I'm going to go back to just cheese sandwiches and said we want 5 and we want 5. Look what happens. I get 2 sandwiches, 1 leftover bread, and 3 leftover pieces of cheese. So we can go ahead and fill that in on our lab sheet. So 2 sandwiches, 1 bread, 3 cheese. Okay, and it's going to go pretty much the same for all these. So I want you to take some time, play with the simulation. You can come back and check your work once you've filled in the rest of this table. Welcome back. Did you get stuck when you got to right here? If so, I'll give you some more hints on these ones. So this time they didn't tell you how much you're using, but they told you what's left over. So they're saying that there's 2 sandwiches with 1 piece of extra bread and no pieces of extra cheese. So let's try and figure that one out. And if you haven't noticed, if you hit this little orange rewind button, it resets it. So let's see. There's 1 sandwich, and they said we want to get 2 sandwiches. So Okay, there's my 2 sandwiches, good. But now I've got to get something else specific. They want 1 excess bread and 0 excess cheese. So how do I do that? Well, let's try that. Yep. So 5 pieces of bread plus 2 pieces of cheese will give us 2 sandwiches, 1 bread, no cheese left over. So 5 slices of bread and 2. So 5 and 2. Now try this next one on your own. Come back and check it once you've got it. So what kind of ingredients do we need if we have 6 pieces of bread used, getting exactly 3 sandwiches, and having 4 slices leftover cheese? Here's what I got. So 6 slices of bread plus 7 slices of cheese will give me 3 sandwiches and 4 leftover pieces of cheese. So 6, 7, and 3, 0, 4. So 6, 7, 3, 0, 4. Now, how do I know this has to be 0? Because they told me there's exactly 6 slices and 3 sandwiches made, and we know that there's 2 slices per sandwich. That's how we know there's no leftover excess bread. And plus, if we went through and we added up an extra one, well, now that's going to be 7. Okay, so that's page 1 done. Let's look at page 2. So let's look at some real chemical reactions this time. Now let's work with real chemical reactions, one that creates a very entertaining boom. So we're going to go to part 2, and we're looking at how hydrogen and oxygen combine to form water. If you remember, this was back from chapter 1 and chapter 2, when we collected that gas in the upside down test tube and lit it with the burning splint. There's a big pop. Exact same reaction. So in our simulation, we need to go to the real molecules, and we're starting right here where it says make water. Before we start playing around here, let's get the balanced chemical equation. The ratio is 2 hydrogen plus 1 oxygen will give us 2 water. So 2 to 1 to 2. So let's fill that in. So the ratio is 2 to 1 to 2. So 2H2 plus 1O2 is going to yield 2H2O. And then over here, these are just whatever excess is left over. So let's do a couple of these and see what we get. So 4 and 4. So 1, 2, 3, 4. 1, 2, 3, 4. What do I get? That gets me 4 waters, but then 2 leftover oxygen. So 4 waters and 2 leftover oxygen, and we used up exactly all of the hydrogen. Okay, I want you to pause the video, try some more of these, and I'll check back in with you. Some of them will get trickier down here, and we'll figure that out together. Welcome back, guys. So here's your first 1, 2, 3, 4 problems. Did you agree with me? This is maybe where you got into some trouble because it asked for 9 moles and 8 moles. If we go to the simulation, it maxes out at 8. So what can we do? Well, we can use our stoichiometry know-how, and we can work through this problem. So if we look at the ratio 2 to 1, I need twice as much oxygen, or twice as much hydrogen as I need oxygen. So what do you think I'm going to run out of first, 9 or 8? If I'm going to use up all 9, I would have to have at least 4.5 of this, which I do. If I'm going to use up all 8, I need to have double. I need to have 16 of this. This is what I'm going to run out of. So let's say I'm actually going to use up all 9. We'll kind of do a BCA table, and there'll be none left over. How much of this will I use up? I'm going to use up minus 9 times the ratio, which for this problem is 1 over 2. And what's 9 times 1 over 2? That equals 4.5. So if I had 8, and I'm using up 4.5, how much is going to be left over? Okay, well, 8 minus 4 is 4. 4.5 is going to be 3.5. Okay, so I know that there's going to be no hydrogen left over, and there's going to be 3.5 excess moles. See, this is where it switched to moles. If that had been molecules, could I have had 3.5 oxygen molecules? No, but I can have 3.5 oxygen moles. Now, how much water is produced? I'm going to be creating 9 times the ratio of water to hydrogen, which is just going to be 2 over 2 right here. So 2 over 2 is 1, 9 times 1 is 9. So we can actually figure that one out by using our stoichiometry. Okay, so you see we've switched over to moles now here. So let's see if we can work some of these out. If we want to use 4 oxygen and get 1 water with no hydrogen left over, let's see what has to happen. So 4 oxygen. Let's clear all this out. And they said 1 water, right? Okay. 4 oxygen, 1 water, no hydrogen left over. Did we do that? I didn't make a water yet. What's going on here? Let's add another. Uh-oh, that got me 2 water. Is it possible to do this using my simulation that I have set up like this? It doesn't look like it. Why do you think that might be? It should work, but I think we've got a little snag in the simulation. So let's go back to our old trusty stoichiometry friend and work this one out on our own. Okay. So if we are going to make only one, we clearly didn't use up all four of this. Okay. So 1 is going to be equal to the unknown number of hydrogen, this must have been my limiting reactant, times the ratio of water to hydrogen, so that's going to be 2 to 2. So what must my question mark be? What times 1 is 1? 1. There must have been 1 water plus 4 of this. That'll give us our 1 mole of this. We'll use it all up, and how much oxygen will be left over? Okay, well, let's figure this out. 1 times, my ratio is 2 over 1. 1 times 2 over 1 would be 2. So we had 4, we used 2. There's going to be 2 left over. That one we had to go to stoichiometry. The simulation didn't work for that one. Now hopefully it works on the next one. 4 and 2. And then nothing else is given. Okay, figure that one out. Okay, 4, 1, 2, 3, 4, and 2. Oh, works out nice. So if we have 4 hydrogen and 2 oxygen, we get exactly 4 water molecules. Nothing left over. We've just made a double batch essentially there. So let's fill that one in. So 4, 2, we're going to make 4 water molecules and nothing left over. Now, let's see what happens if we only have 2 moles of hydrogen. We're trying to solve for this, and then there's 2 moles of water with no leftovers. So let's see what goes on with that. Okay, there's 2. Now we want to get no leftovers. Ah, look, that did it. So 2 hydrogen, that gives me 2 water, no leftovers, so we just need 1 of those O2. So this is going to be 1. Perfect. So we had a little bit of problems, but I think using our stoichiometry know-how, we could solve those. So notice that the labels change from molecules to moles. This does not change the mole ratio. So remember, we can use that mole ratio to talk about either individual molecules or moles of molecules. As a mole is simply a large number of molecules. How many molecules is 1 mole? Your brain should be shouting out the 6.022 times 10 to the 23rd number right now. That is 1 mole, Avogadro's number. Okay, let's go to part 3. This time we're going to try producing ammonia, a very important chemical in industry and farming. So what is the mole ratio for the production of ammonia? Let's go back to our simulation. We're going to go to make ammonia. And you can see it's 1 nitrogen plus 3 H2 gives me 2 NH3. So 1, 3, and 2. So 1, oops, wrong pen right here. So 1 nitrogen plus 3 H2 plus 3 H2 is going to yield 2 NH3. Here's my recipe, okay, here's my reactants. I'm adding those together to get the ammonia, and the ratio is 1 to 3 to 2. Okay, so let's go through and try some of these. So I want you to pause the video, try some of these on your own now that I've helped you through the first 2, and we're going to come back and check our work in a minute. Welcome back, ChemStars. Did you get the same answers as me? Did you get confused in this one that only says 4? This one, you can go whatever direction you want to. So you can fill in anything you want as long as we have 4 moles of H2. So let's take a look. So if we reset this and just, back to make ammonia, make 4 moles of H2, we don't get anything. If you want to leave everything as zeros, you can. If you want to play around and put in other numbers, you can. For the sake of it, I'll just leave this as 4, nothing's made, and 4 leftovers. So you could say, okay, nothing, 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 and 4. That's totally possible. Okay. Let's try the next one together and see how far we get. So let's looking at combusting methane now. So 1 methane plus 2 oxygen gives me 1 CO2 and 2 H2O. So 1, 2, 1, 2. So 1 CH4 plus 2 O2 is going to produce 1 CO2 plus 2 H2O. So here's my recipe, my balanced chemical equation. And over here are going to be the leftovers, the excess. Ratio is 1, 2, 1, 2. Okay, so make sure on your simulation you're set to the combust methane. Try the next couple, pause the video, come back, and let's check your work. Welcome back. Did you get this for combusting methane? And did you maybe get a little bit stuck when you got here? I'm here to help. So let's look. If we produce 1 CO2 and 2 H2O, that's where we want to start with. So we're going to try and get 1 and 2, and we'll worry about the excess in a minute. So 1 CO2 and 2 H2O. So we want to get 1 CO2. Oh look, there's 1 CO2 and 2 H2O. But now let's worry about the leftovers. It says we need to have 2 methane extra and 1 extra oxygen. Okay, let's get the oxygen fixed. Okay, there's my 1 extra oxygen. And how many methanes did they want? They wanted 2. So let's bump that up. Bump that up again. Okay. So 1, 2, 2, 1. 1, 2, 2, 1. Yep, that looks good. So that means we need 3 moles of methane and 3 moles of oxygen, and we'll get those reactants, those products and those leftovers. So 3 and 3. And then let's look at the last one. Now they want to make they want to make 6 water, and then they want to make having 1 excess oxygen. I want you to try that one, then come back and check. Okay, so for that last one, the only thing we know that they want is 6 water, no leftover methane, and 1 oxygen. Here's what I got. 6 water, no excess methane, 1 oxygen. And to do that, I need to have 3 methane to start with, 7 oxygen, and that will give me 3 CO2, the 6 water that I wanted, and the no methane left over, and the 1 oxygen. So 3, 7, 3. Let's fill that out. 3, 7, 3. So here's the last part of just the lab portion. I want you to go and play the game. So if you go to the bottom, go to game. There's 3 levels that you need to progress through. Let's just start with level 1 and show you how it works. So here's the balanced chemical equation. And then we want to see if we can try and get everything to match. Okay, so I'm just going to randomly click some things. Let's see if that was right. Oh no, that wasn't right. That means that I need to start over. Or you can just maybe hit the undo button there. Okay, so on this one, they want to get 1 nitrogen left over. Okay. Let's see if that works. Yay, got it right. So as you go through that, you can go to the next problem. I want you to record your score and your time, and you're going to fill that in down here. Don't wait to be great, as Mrs. Vanderwally always says, and that's the end of the lab. But it's not the end of your lab worksheet. The very last page is going to go through and review, okay? This is the review of Chapter 9, Stoich. This, we're going to have to use some BCA tables, and you're going to have to be using all those good mole ratios we taught you, okay? So I want you to pause the video, try some of these on your own, and then we'll come back and check it all together. How'd you do on that problem? Let's look at number 2. All they said was, for the reaction, determine how many moles of chlorine would be needed to react with 3 moles of P4 phosphorus to try to use up all the phosphorus. So what we're looking at is if we have 3 moles of this, the coefficient here is really 1. Am I just not making a triple batch? So what we can do, just triple everything. So how many moles of chlorine do we need? 18. It's as easy as that. But now things don't get quite as easy. We've got some excess and limiting reactants. So here's where we want to probably sketch out a BCA table. Let's work smarter, not harder. So we need 6 times as much chlorine. So if we're going to use up all 5 phosphorus, and we need 6 times as much chlorine, we would need 30 chlorine exactly. Do we have that? No, we don't. So phosphorus can't be limiting. It must be the chlorine that's limiting. So we're going to use up all that chlorine, and let's figure out how much PCl3 is produced. We're going to be producing 22 times the mole ratio, which in this problem is 4 PCl3 for every 6. So 22 times 4 over 6. 22 times 4 divided by 6. We're going to get 14.66 moles of the product. So 14.66. That's going to be your moles of the product PCl3. How many moles of P4 left over in excess? So, there he gives us a hint. So we knew we picked right. So let's see. We're going to be using up minus 22 times the mole ratio, which on this problem is 1 over 6. So 22 divided by 6. 22 divided by 6. I'm going to be using up 3.66. So 5 minus 3.66 is going to give me 1.34. So I'm going to have 1.34. It's going to be 1.34 moles of P4 excess left over. So I want to label, this is my excess, this was my limiting reactant. Limiting reactant column will always go to 0. How many moles of Cl2 are left in excess? None. It was limiting. Good. Okay. One more problem, then we're finished with this. In reality, reactants don't have to react in perfect whole number of moles, like we just saw up there. In a two-reactant synthesis reaction, usually one reactant gets entirely used up and determines how much product is made. That is the definition of our limiting reactant. That's our limiting reactant definition right there. Even if that means using fractions of a mole of a reactant. For instance, when solid metallic aluminum, so metallic aluminum, and then red liquid bromine are brought together, they make a white solid aluminum bromide, according to this reaction. So let's say if 5 moles of the aluminum was reacted with, oops, I got the wrong color. Hold on, let's color code properly here. 5 moles of aluminum was reacted with 10 moles of bromine. All 5 moles of aluminum would react, but with only 7.5 moles of bromine because of that 2 to 3 mole ratio. This would produce only 5 moles of the AlBr3, leaving 2.5 moles of excess bromine behind. So this right here, this is our recipe. This is where we pull all the mole ratios from. So now let's assume that 3 moles of aluminum and 4 moles of bromine react. We're going to show some work. I'm going to probably squeeze our BCA table over to the side maybe. I don't like how this is formatted, so let's just try our best. So we've got before, change, and after. We have 2 aluminum plus 3 Br2 is going to yield 2 of our product AlBr3. And this, we're kind of setting off. That's my recipe. Let's put in what we know so far. We know that this is happening. We know that's happening. And they said assume 3 moles of aluminum. So we're starting with 3. And 4 moles of bromine. Okay. What do you think is going to run out first? Do you have any idea? Aluminum? Bromine? Not sure? Okay, let's just pick the first one and see what happens. Let's say we're going to use up all 3 of the aluminum and there'll be none left over. How much bromine will I use up then? I'm going to be using up 3 times the ratio, the mole ratio up here from bromine to aluminum. Oops, that should have been black, not purple. So let's see. 3 over 2 times 3. So 3 divided by 2 times 3. Uh-oh, I'm using up 4.5 right here. That means I have negative 0.5 left over. Can aluminum be limiting? No. So it's not aluminum. It must be bromine. So if you ever get a negative, that just means you chose poorly, and we need to go back and fix our mistake. So now that we know this, let's just erase that work here. Erase it as best we can. Oh, this is frustrating. Okay, so let's label what we just learned from that. So we just learned that bromine must be limiting. That means we know that this column is going to go to 0. In the reaction, I'm going to use up all 4. There'll be none left over. How much aluminum is going to get used up? 4 times the mole ratio. So 2 aluminum for every 3 bromine. So 4 times 2 over 3. So 2 divided by 3 times 4. I'm using up 2.66. I'm starting with 3. Can I take 3 minus 2.66, still get a whole number? Yep. So 3 minus 2.66, and I'm going to get 0.34. Now I'm kind of rounding here. It's fine. 0.34 of excess aluminum left over. So which chemical must be the excess reactant? Aluminum. Oops, mistake up here. Let's fix that. Our bromine should have been Br2. How much in moles of aluminum bromide gets produced? So we go back to that coefficient from the limiting bromine. So 4 times the ratio of the unknown product, aluminum bromide, to the bromine. So 4 times 2 over 3. We already did that math over here, but if you've forgotten, here it is. 2 divided by 3 times 4, we're going to get 2.66. So we get 2.66 moles of the product. 2.66. So if all the limiting reactant gets used up, that's the bromine, how much excess is left? Oh, golly gee. We already did that work. Easy peasy. 0.34 moles of excess aluminum. So we can answer all those questions with one simple BCA table. So that's the end of our PhET lab. I hope that you had some fun playing the game, and I'll see you next time. Bye, guys.